Okay, so our next talk is by Alvaro Faria on an application of dynamic Bayesian star models to electricity loading in Brazil.
This is a joint work with Alexandre Santos, who was my PhD student and finished off his PhD last year. So we developed a dynamic Bayesian smooth transition autoregressive model. And one of the applications is for, sorry, I meant that is the microphone. Hello. One of the applications was on the electricity loading in Brazil. So I'll start this talk by outlining, I'm describing the star models for nonlinear stationary data. That's what they were originally developed for. Let's see if this works. I will then introduce the dynamic Bayesian star models, which applies to non-stationary data, and which components can vary in time contrary to the original star models. And then I'll describe the application to the hourly electricity load data. The star models, they are basically a linear combination of autoregressive models which compete. They are called regime. So autoregressive regimes that compete at each time. And they are weighted by what is called transition function. And of course, the S is for smooth. This transition function is conveniently chosen to be a smooth nonlinear function between the two regimes. So there are two types that are mostly used of the conveniently chosen nonlinear functions. One is the logistic, and the other one is the exponential. There are other functions, but those are the most commonly used. That function is a function of what's called transition variable, which can be either a past value of the time series of interest or an external variable that can, as is in the case of the application I will describe later, we use temperature as a transition variable because of its effect, nonlinear effect on the load, as we'll see. So in the star models, autoregressive coefficients, the error variance, the error variance, and the smoothing parameters, they are all static. Gamma. Here is this smoothing parameter that you can control the degree of smoothness between the change of regimes at each time. Obviously, it requires the data is made stationary before the application, and it uses nonlinear least square methods based on polynomial approximations of the smooth function to estimate the parameters. Most applications of this type of models are in economic time series. They've been shown to particularly work well for data exhibiting asymmetric cycles, which the linear models are not very good at. So another benchmark application, which we also use, Alexandre used in his thesis to compare with, is the Canadian link data, which is non-economic, is ecological data, the capture of Canadian link in Mackenzie River. But I will not describe that application here. So the DB star models, dynamic Bayesian star models, they are state space formulation of the star where we approximate the transition function by a polynomial function, basically. In this work, we use the Taylor series expansion of the, let's say, logistic transition function, and also spline approximation of it. So the approximation in the dynamic Bayesian star models are at the modeling stage, while the star is on the estimation stage. So they basically are transformed into a polynomial dynamic linear model of Western Harrison. And the parameters are sequentially updated by Kalman filter in the usual way. including the observational variance that can now change in time. The order of the autoregressive regimes are considered to be known, and you can model individually all the components such as trends, seasonality cycles, and they are applicable to nonlinear on stationary autoregressive processes. This is the transition function, and this is the approximation we use. We managed to separate the polynomial on the transition variable ISBI here. Usually for the Taylor series, for example, this is ST to I to the power of I, and those are the coefficients which are functions of the smooth transition. So they can change at each time contrary to the static star models. And if you'd like to look at some references, I'll give a list at the end, but there's this references there. So basically, once the approximation of the transition function is made, and you choose the approximation you'd like to use, we chose in this application both, and compared them, you have the normal observation equation formulation. In this case, it's a Gaussian process with the prior for the mean. We use a discount factor for the observational variance, and which is unknown, and inverted gamma with the appropriate parameters, and using the sample variance to sequentially update. Contrary to the previous talks, I mean, we tried as much as we could here to preserve the analytical tractability so that it could be computationally efficient in terms that you could use for high frequency data, and the computations are quite fast. So that is the idea here. Instead of using MC approximations or particle filters, we do the approximation of the transition function, resulting in this polynomial, and Kalman filter does all the updating. The system evolution, again, we set the prior covariance, and it's a double discount model. In particular, this one we applied for the load data, electricity consumption. This is the model formulation where these are all known. The Fs are the polynomial functions of the transition variables, and GT, of course, is the system evolution, also fixed, and the priors basically parameters are set for the observational variance and the discount factors. So this model allows uncertainty handling and data simulation, learning from the data sequentially. Analytical approach, as I said, implies fast computing. Expert intervention is allowed, and it's suitable for intrinsically non-stationary data that cannot be made stationary to be used by other models. The discount factor setting allows change in the degree of adaptability to data. These are another advantage is that compared to the classical stars, they are parsimonious models, so you can model particular components in the most parsimonious manner possible. So usually low IR orders for level and trend, as well as for seasonal and cyclic components. Changing cyclic period can also be modeled explicitly. So I'll go now describe the application. You can see the map. You should be seeing a map of Brazil with highlighting the southeast and the central west regions in Brazil. So this data is hourly time series of hourly load of those regions in Brazil. So they are aggregated data for the whole region, or the two regions actually. So we have the data starting from the 1st of January 2003 to 30th of, it's a 7-year span of data, 62,088 observations. And we used average temperature as the transition variable. So this is the data. The data shows a long-term trend as can be seen in that plot there. It looks like there's an increasing variability as well, and it looks like a linear increase, a linear trend. And this is a typical weekly cyclic pattern. Cyclic here used to describe within the day and within the week repetitive behavior. So this is a slice of the time series showing for the winter, for the summer, for the winter, in Brazil it's the contrary, I mean, the summer and winter, how the cyclic within day and within week behavior changes from one season to the other. So you have this changing cycle. So we have 24 hours within the day cyclic periods as well as within week. For this data, the seasonality, which would be the within year variation, is picked up by the temperature, actually. So it saved us in the name of parsimony. We tried a seasonal model, but it didn't make much difference, really. So it also presents yearly cycles, as I said. So cyclic patterns change in time with the season. Harmonics are time-dependent components. So basically, the polynomial GLM is an harmonic one for this application. We also have a harmonic component to represent the cyclic periods. Second order non-stationary present with changing variability. So this is a plot of how the temperature how the load actually varies with the temperature. So you can see here a smooth line of representing the relationship, which is fairly linear within the range of temperatures, and then it increases fastly at higher temperatures and decreases not as fast as it increases, but this decreases slightly for lower temperatures. Usually in northern hemisphere countries, you'd see a U-shaped relationship between temperature, between load and temperature. So this is the general formulation for this application. You have an approximation of a logistic star, where the temperature in the previous hour is used as a transition variable. Trend, cycle within the day, within the week, holidays. Here, I would say perhaps calendar would be more appropriate terminology to adopt there, and the error term. So this is, we had three competing models. Model A is a Taylor series dB star. So we use the Taylor expansion of order 3 to this model to approximate the transition function of this model. Model B, it's a spline model that uses truncated basis truncated power basis model. And model C is the B splines approximation. And they have AR the degree of the autoregressive models competing are 1. Delay is 1, this is this one for the time. And 2 harmonic components for each of the cyclic variations within day, within weeks, and some optimal values obtained quite close to one of the discount factors. So we have here a plot of the posterior mean of the trend, which shows differently from the apparently linear trend in the model, a linear trend in a sense, and then a stabilization or change in level after a certain year. So that is what the posterior mean of the trend picked up from the data. This is the posterior mean of the periodic components. Again, for the corresponding to the time slices shown before for the data, you can see the changing of the posterior means of those components for different times for those 2 weeks, actually, for each of those 2 weeks. So to compare, this is the data, and these are the components for the 2-week period there. So not as accurate, but it captures though the repetitive behavior and the change in the repetitive behavior from one week to the other. In terms of forecasting, the last 30 days, June 2010 was left out, and the model was used to, those three models were used to produce forecasts for one step ahead forecast, well, not one step ahead, one step ahead during fitting, but during application, out of sample, and the B-spline model produced a slightly better performance than the Taylor between the three models. So this is the log-like likelihood. So these are the plots of the 1 hour ahead forecasts. You can see this is for the 3rd week in June. You can see that the model, and of course for model C, which was the one that performed better in terms of forecasting statistics. So you have a quite actually good forecast. The dots are the observations, the actual values, and you have the 95% prediction intervals around the line. And you have also the following weeks. And in particular, June 2010 was the Football World Cup in South Africa. So you can see some changes in the electricity consumption at those days. You can see, for example, a normal, this is the normal repetitive behavior for that week. But that day in particular, in the middle of the day, or in the afternoon, to be more precise, there was a considerable drop in the consumption. The same thing happened here on the, you can't see very well, but that was Monday, so on Sunday. So there was a football match on Sunday, and I have written down, I think that was Brazil against North Korea at 3:30 in the afternoon. Then the next one, if I don't, I think Ivory Coast was the net one, and that one was Portugal. And finally, in the last week of June, you had Brazil playing Chile. So yes, and you can see also the increasing prediction intervals as the horizon increases in time. So these are the references I mentioned earlier for those who are interested. I could carry on to show the Canadian link application, but I'm not sure we have time. So I included, because Lopez and Salazar, Hildebrand, Lopez and Salazar developed a Bayesian model for the static, though, star. And the Canadian link we compare, which is a benchmark model, data, sorry. We compare our models with Lopez and Salazar and also with the classical static, and they outperform, I must say, the other methods. Although we had to do some, because those are static, they fit the whole data. Now our models are sequential, so we had to do a retrospective analysis for comparability reasons. But that's all I have to say for now.
Thank you. Are there questions?
Hi. Your predictions were made for were one-period predictions for the next hour. Is that correct? And if so, have you tested the predictive power of the model for longer periods?
Yes. I mean, usually I was told and I learned that many electricity companies, they would like to have 24 hours ahead on an hourly basis forecasts, so they can act from one day to the next. We did, but I haven't produced the plots yet. We had some problem running, out of memory problems in running R, so it's implemented in R, but I managed to save now in file because of the large arrays. And what I just need to go there now and calculate the statistics for measuring the performances. But yes. you can do that, yes.
Are there other questions? So I was just wondering if you compare it against just a standard switching model, not the smooth transition, but just like an abrupt change to a new model.
Sorry, I couldn't hear you.
If you compare it against a just standard switching model, not a smooth transition, where you have a switch to a new process after the time point, did you compare it to something like that?
No, we haven't. Just with those, the classical star and the Bayesian version of the classical star, static models, and with our sequential model. We're thinking now in looking at the use of particle filter, for example. So if they are fast enough to calculate, because those, for the hourly data, and in some instances you have half-hourly data, so you need the model to run quite fast on a sequential basis. One thing that we lose here, but you may lose depending on the orders of the autoregressive regimes, is the original interpretability of the parameters of the star model, because they are turned by the expansions into polynomial approximations. And that requires a solution of a system of polynomial equations at each time. So if interpretability in the original parameters is desired, you do have to solve. And as I said, I know that for low orders, we have done for the Canadian link data, we could obtain the estimated changes in the parameters of the corresponding star.
I see.
But I don't think that's a general. For higher orders, perhaps larger than 5, you probably struggle to find solutions to the system of equations. So.
Okay, are there any other questions? If not, let's thank the speaker again, and that's the end of this session for today.
Thank you.